I'd like to tell you a story today about plastics, about sugary things, that's what confections means, and how these are related to material science and chemical engineering. And I think to orient ourselves, we should start with the famous movie, The Graduate, which was released in 1967. Benjamin is somewhat of a lost soul. He's just graduated college. He doesn't really know what his future life direction is going to be. Everybody wants to give him advice. All of his parents' friends are interested in weighing in. And Mr. McGuire has some particularly insightful advice for Benjamin. And so Mr. McGuire says, I want to say one word to you, just one word. And Benjamin replies, yes, sir. And Mr. McGuire says, are you listening? And Benjamin says, yes, I am. And then Mr. McGuire says, plastics. There is a great future in plastics, okay? Being in this industry, of course, we, in my group, buy into this dogma, and I'd like to tell you a story today about plastics. Now, we commonly call plastics by a different name. All of us, if I said the word plastics to you, you can conjure up images of things you interact with on a daily basis, like water bottles and bags, etc. We call plastics polymers because plastics are made of polymers, okay? Polymers are very long molecules, and they have many, many repeat units of building blocks that we call monomers. Here's an example of a monomer that's called styrene. This is a small molecule. It's like ethanol. Ethanol is alcohol, which we sometimes enjoy drinking. Styrene, I wouldn't drink, but it's a monomer. It's a small molecule like ethanol. When we apply chemistry to a certain kind of monomer, we create a polymer from it. And I'd like to point out a couple important things about this. First, for the rest of the talk, we're going to illustrate polymers as squiggly lines, and we're going to remember that these represent long molecules, and the color is going to be used to tell us something about the chemistry, something about the monomer that was used to form that certain kind of polymer. We'll see different colors appearing shortly. Second, I'd like to point out that since these are long molecules, we'll use this letter outside of the parentheses to indicate how long are they. So this tells us how many monomer units are repeated to form a single polymer chain. Now, N can be small, say on the order of 10, or N could be very large, in the many thousands. And it turns out that most of the commercial products you use that are plastics have very large N, on the order of thousands. This polymer is a very well-known, very popular polymer. It's called polystyrene. You might know it as styrofoam. It's used in things like food packaging. Now, I want to turn to another fact about polymers to motivate the rest of this talk, and that's most polymers don't mix. And you can probably appreciate this in the context of recycling. If you think about recycling, here in Santa Barbara we have mixed recycling. We dump everything in the same bin and it gets sorted later. Some places don't have mixed recycling. For example, you might have to segregate paper and glass and metal and then plastics. Even in the case when you're doing the separation and you're creating a bin called plastics, not all plastics are the same. There's many different kinds of chemistries used to create different plastics. For many different reasons. They have wildly different properties, okay? If you zoom in on a plastic recycling bin, you might see a familiar kind of symbol. These represent the different kinds of polymers that you might recycle. And so oftentimes plastics have these different symbols to tell you what they are. Now, what do we mean when we say polymers don't mix? If we were to take all of these plastics, which have been separated from metals and glass and paper, and we were to try to melt them down together and form a new product, that new product would have terrible properties because the polymers don't mix. Let's illustrate this by means of an example. Imagine you take a water bottle, which is polyethylene terephthalate, number 1 on the recycling numbers, and say you throw it with some styrofoam coffee cup, which is polystyrene like we saw on the previous slide, number 6, and you throw them together in a plastic bag and then dump that in the recycle, where the plastic bag is low-density polyethylene, number 4. And you try to form a new material out of this. It will phase separate much like your salad dressing. When you leave your salad dressing for a while and it creates multiple phases. This phase separation leads to terrible properties. So nobody recycles polymers and melts them all down and makes a new material. You have to separate them. And usually the recycling facilities separate them. And that takes a lot of effort and energy and money to do. So you might think that because we're saying polymers don't mix, this is always a terrible thing. We take advantage of that fact in our lab. We actually exploit it. We exploit it with a class of materials known as blockopolymers. So notice now, we're illustrating one long molecule with two different colors. That means we're creating it from two different constituent chemistries, a blue and a red, and we're linking these polymers together as depicted at that black circle, which is the junction. So there's two different blocks, and we have a block copolymer. You might imagine that the blue is polystyrene like we saw before. Another commercially important polymer is polyisoprene, as illustrated. Okay? These types of materials self-assemble. They make ordered structures. A few of them are depicted across this illustration. These ordered structures arise because the red and the blue, they don't mix. They want to phase separate. But if you think back to the salad dressing example, the phase separation in salad dressing is on a very large scale. You can see it with your eye. That's what these polymers want to do, but they can't because they're linked together. And so the structures that they form are quite small. They're on the molecular length scale instead of the visible length scale. Let's gain an appreciation for this size by drawing a line that represents different lengths. On the bottom is meters, and on the top are units that are related to meters, micrometers, nanometers, angstroms. And let's place some objects or some things that we're used to thinking about or seeing, or at least appreciate. This is a micrograph of a human hair. Our hair, one strand is about on the cusp of what we can see with our eyes. Right? You can see it, but it's close to being not observable. The diameter of a human hair is on the order of 50 microns, so it's roughly 10 to the minus 5 meters. Visible light can be thought of as a wave, and if you treat it as a wave, it has a wavelength. The wavelength depends on what color you're talking about. Red, blue, Roy G. Biv, right? The wavelength of visible light is somewhere around 500 nanometers, give or take. Significantly smaller than human hair, somewhere like 10 to the minus 5, 10 to the minus 6 meters. Viruses have a characteristic size, could be spherical. The size is roughly 50 to 100 nanometers, somewhere in this range, which is about 10 to the minus 7 meters. Atoms are a nucleus. They have a cloud of electrons around them. If you ask what's the approximate size, the diameter of an atom, including its electron cloud, it's approximately an angstrom or a couple angstroms. Where do blockcopolymer structures fall on this length scale diagram? Well, they're molecules. We said they're pretty big molecules. Molecules are made of atoms, so it's got to be bigger than an atom. It turns out, depending on how you synthesize them, they're roughly in the range of 1 nanometer to 100 nanometers, or a little bit bigger. Let's say the average is around 20 or 30 nanometers. Depends on the synthesis. This gives rise to very interesting and useful properties. These kinds of materials are all around you, whether you realize it or not. For example, synthetic rubbers, like many of you are wearing in your shoes, are made in large part from blockopolymers. Pressure-sensitive adhesives, like Post-it notes. You peel the Post-it note off the pad, you press it against a new surface. That strip of glue at the top of the Post-it note, which attaches to the new surface, is a pressure-sensitive adhesive. It sticks when you apply pressure. Some of those are made out of blockopolymers. They're also put into roads. Now, this is Santa Barbara. You might not be able to relate, but I'm from Minnesota, and the temperature swings a lot more than it does here, even in June gloom. And so the temperature can get quite hot, and then it can get quite cold. And it does this by the season over and over and over again. When you add block copolymers to roads, it can toughen them and make them more impervious to these temperature swings and make it harder to damage the road over time. These are big businesses. For example, the synthetic rubber business is on the order of $20 billion a year. Okay, roads, big business, etc. Block copolymers are also being looked at for other technological applications that haven't exactly been commercialized yet using block copolymer materials, but that they could provide added benefit for, and people are very interested in. For example, lithography. The integrated circuits in your cell phone are made by a process called lithography. It's also used to make computer chips in laptops, and it's also used to make storage memory like disk drives and flash memory. Okay? So the process of lithography, everybody wants a faster computer, everybody wants a higher density disk drive. How do you do that? You make your transistors smaller and smaller and smaller. You have to have a way of making those structures. People are really interested in using block copolymers for that because the lower limit of the self-assembly is about a nanometer. That's a lot better than they can do with the optical processes used today to make computer chips. As another example, water filtration. Water is a really important resource, obviously critical to life. If you think back to the previous slide, we said that viruses are about 50 nanometers in size. But you can make little pores in membranes using block copolymers that are, say, 5 or 10 nanometers in diameter. So if you can push water molecules through those pores, you would block viruses from moving through. They're just too big. You might be able to make really interesting water separation and other kinds of membranes. A third and final example is drug delivery. If you get sick and you have a tumor and you want to kill the tumor, you really want to deliver toxic drugs only to that location. You don't want healthy tissue, healthy body parts to be influenced by these drugs. And so you need a way of targeting delivery. And people are trying to take block copolymers, encapsulate drugs within one of the domains, like the red chemistry domain, surround it with blue, where the blue could interact with blood, and it could facilitate the movement of the drugs only to the desired location. This gives you some sense of the importance of the field overall, and the key across all of these applications is this connection between structure, like we saw in the previous slide, and properties, where the properties, the desired ones, vary depending on what you're trying to do exactly. Here's an example of the structures we just saw 2 slides ago that we said block copolymers can form. Notice they look spherical, some of them are cylindrical. This gyroid is a network. It's actually an interpenetrating network of red and blue. And then you can make lamellae, which are alternating sheets, and then you can make the same structures except with the opposite color block being on the inside. What I'd like to focus in on is the sphere phases. From 1980 to 2009, there was significant work in this field looking at these structures. And the types of spherical structures that were formed are only 2, and essentially only one, body-centered cubic spheres. This is an image of what's called a unit cell. So it's the building block of the structure that's repeated in 3-dimensional space. Okay, single building block. And in this body-centered cubic structure, you have a little sphere at each of the vertices of the cube, and then one in the middle, right in the middle of the cube. In the face-centered cubic structure, you have spheres at the vertices, and then you have a cube at the center of every face. You can see here's one at the top face, the front face, side face, etc. These were the only 2 sphere-forming structures known. And again, these structures are important in roads, etc. In 2010, Sang-Woo Lee, who's now at RPI, made a startling discovery, a new sphere phase. Hadn't been seen before in this kind of material. It's called the sigma phase. And I think you can pretty easily appreciate that this looks a lot different than the body-centered cubic spheres or the face-centered cubic spheres. Very complex. There are 30 different spheres in this unit cell. And then this thing, again, fills space over and over and over in X, Y, and Z directions. So we were motivated by this to try to understand why. Are there other structures lurking out there? If so, how can we design these types of materials to make new kinds of structures? Because we know structure is at the heart of applications. And that's what we set out to understand. To appreciate what we're going to try to make, we need to spend a minute thinking about how polymer chains actually fill space. We've been drawing polymers as little squiggly lines, pretty extended. They've got a little bend here or there, but we've been drawing them as being quite linear and extended. This is unphysical. This is not how polymer chains fill space. They actually make coils, like a piece of cooked spaghetti. It coils up on itself. And these coils you can characterize, for example, by their radius. And let's call the radius B. Here with a little a that's red, because the characteristic size of the coil depends on the chemistry that you use. For example, if we came in with a different chemistry, blue instead of red, the coil might have a different radius. Let's call it B with a little subscript B. Imagine you make a block copolymer out of this now. If the two coils, the red and the blue, happen to have the same size, they fill space about the same on either side, and you can have a flat interface. But if you make one of the coils a lot different size, bigger, you tend to bend the interface towards the big coil. This has been predicted to be really important for those complex phases, like the crazy sigma phase that we just saw in the previous slide. So we were motivated to study this. There's another way you can do this. You can do it, instead of thinking about coil size, you can think about polymer architecture. If instead of having one blue chain connected to one red chain, you have two blue chains connected at the same junction to one red chain, you have something called a mycto-arm star polymer. This also tends to bend the interface towards the red, and if you add even more blues connected at that junction, you further bend the interface. And we were really motivated by these two ideas to ask, can we tune the architecture and the coil size and make new kinds of phases, new kinds of structures? And I'd like to start by emphasizing a story related to architecture, because from a polymer chemistry perspective, it's pretty hard to make materials that look like this. We realized that quickly. This is an example of a book cover published last year, all about mycto-arm star polymers, hundreds of pages long, different ways of making them. They're all different. None of them are easy. We asked the question, can we make it easy? If we make it easy, remember, we're not trying to study the synthesis. We really want to study the structure. We've got to have access to a lot of different materials. That's where Morgan Schultz comes in, a very talented postdoc here at UCSB. And she said, well, wait a second. Here's the goal. Let's say we're trying to make an AB2 type of mycto-arm star polymer. Let's think about that black dot for a second in the middle at that junction. What if we pick molecules to make that black dot first, and then we grow polymers from it? And what if instead of having to make those molecules, we pick molecules that are everywhere, cheap, and easy to find? Well, sugars are everywhere, cheap, and easy to find. This is an example of a sugar molecule. There are many different kinds of sugars. We all like eating sugar. those types are typically sucrose and fructose. It's not exactly the same as this molecule, but they're very closely related. And there are many others. And Morgan said, wait a second, there's two types of functional groups on this molecule. The one in red is called a primary alcohol in the lingo of organic chemistry, and the ones in blue are secondary alcohols. They're both OHs. They have a little bit different reactivity from each other. So if we could turn this molecule into something useful for making polymers, we might be able to make mycto-arm star polymers. I won't belabor the chemistry, but for those of you that are interested, we do a couple transformations and we turn it into this molecule. They're not very hard. Undergraduates in our lab do this on large scale. The real power of this approach now, coming back to the idea of sugars, is, like I mentioned, there's many different kinds of sugars available. Here's an example of other sugars. You'll notice there's a unifying theme between all of them. They're all made of secondary alcohols that have been colored in blue and primary alcohols that are colored in red. They just have different relative ratios of the two. So if we optimize the chemistry for one sugar, the idea is we could apply it to the whole series of sugars and make a bunch of different mycto-arm stars, AB2, AB3, AB4, AB7, etc. Now, again, I don't want to emphasize the chemistry too much, but for those of you that are interested, this is what we actually do in lab. I'll show you one slide of the types of chemical transformations we do. We take this functionalized sugar molecule and we react it with a monomer. Remember, monomers are small molecules. They're the building blocks of polymers. Here's an example of a monomer. It's in a class known as acrylates. These polymers derived from acrylates are found in things like baby diapers, paints, and many other applications. In this case, we use a little bit of a catalyst. Here it's a simple copper wire like you would buy at the hardware store. You can see Morgan has wrapped it around the stir bar. This is an example of the reaction. There's no special precautions. Any of you could do it today. You just walk into lab and mix things together. Very simple. Here's an example of the product that's formed. If you want to just look at the illustration, it has two blue arms connected to that sugar molecule. Here's an example of the polymer chemistry. And then we take this and we react it with a different monomer. This monomer is lactide. We use a different catalyst, and we grow another polymer chain from that primary alcohol. And here's an illustration of the final mycto-arm star polymer. This is the goal. This is what we were trying to make. As an aside, this polymer is known as polylactide. Again, it came from lactide, which is the monomer. And you've probably seen this. There's a decent chance you've actually used it today. This is things like biocups, for example, the degradable and compostable cups, plastic cups that are found. There's also silverware that's made, plastic silverware like forks and knives and spoons that are made from this stuff. If you bury it in the ground, you come back a couple months later, it's gone. It's kind of amazing. It doesn't accumulate like other plastics do in the ocean. This is an example of what the final product looks like. It's a white powder. You can weigh it out. You can do stuff with it. Simple to handle. Now that we've made polymers, we should appreciate a little bit about how to analyze them and think about them. And we mentioned earlier that their size is one distinguishing factor. Polymers are very big molecules. This gives rise to many of the properties that distinguish them from other types of materials. And it's appropriate to draw an analogy with nature. Nature also makes polymers. We're all made of polymers. Things like proteins, for example, as depicted on the slide, are polymers. They're long molecules. The constituent units, the monomers, are amino acids. Nature strings them together in very controlled sequence. It makes long molecules that fold up into intricate structures. And the really remarkable thing is when nature decides to make a protein, a specific kind of protein. Every time it makes that protein, it's exactly the same size with exactly the same sequence. There is zero variability for a given protein. If you were to look at the distribution of the size, there is no distribution. It's a single line. In polymer chemistry, we describe the breadth of the distribution using a variable d bar, and when there's no standard deviation, d bar is equal to 1. So nature does a really good job. Let's say we're trying to make a polymer, like the one we saw in the previous slide, and we're targeting some sort of chain. Let's say it's made of blue chemistry, and let's say we're targeting 500 repeat units. Well, inevitably, as polymer chemists, when we do that, we will get some chains that are shorter and even shorter and still even shorter, and we'll get some chains that are longer and longer and longer. We will have a distribution of sizes. If we're good, the distribution will be centered around an average, what we wanted. If we're not good, as frequently happens, it'll be terribly off. The distribution might look something like this, and this measure of the standard deviation will be greater than 1. Many commercial products have values about 10 or 20. We've measured this for our materials. They're about 1.05. So they're pretty close to nature, but honestly, still really far away. We can't do as well as nature. So I'd like to tell you now about how we characterize the structure. The structure is characterized at things like national labs. This is called a synchrotron. It's outside of Chicago. It doesn't look too impressive from the air. The diameter of this ring is actually 1/4 of a mile. This is a huge building. And it circulates electrons at about the speed of light, like 99.99999% the speed of light. Those accelerating electrons give off X-rays. The X-rays are extremely powerful, and we shoot them into our polymers. And this is an example of what the pattern might look like of the X-rays that scatter. They scatter because of the structure. We can analyze these rings, and we can interpret how the material actually self-assembles. Here's a small example of what we might see. For one of the linear polymers, where we're looking at coil size differences, we've indeed found a new phase already, a new type of structure. You'll notice the distribution of spheres doesn't look like what we saw previously. This is a phase known as A15. It's been seen in other contexts, but not with this type of blockopolymer material. You can take slices of that image and you can look at the electron density distribution within that repeating unit cell. Here's an example of one of the myctopolymers. We've found the sigma phase. Again, the sigma phase had been observed in this type of material, but not in this kind of material before. So it's sort of like a new phase. Again, you can look at the electron density distribution, and the take-home message here is it's pretty complicated looking. These are not simple types of patterns and motifs. So with that, I would like to leave you with this notion that we're really interested in structure. To probe structure and ultimately tune properties, we use polymer chemistry, which involves some small molecule manipulations and then actually making larger molecules out of them. And with that, I'd really like to thank all of the students because they're the ones that actually do this work, particularly Morgan Schultz. Thank you for your attention. Thanks again.